Hello, this video introduces the vector product. Quite often in 3D we want to find a vector that's perpendicular to two other vectors. So for example, I might want to find the normal vector to this plane when I only know two vectors that are in the plane. Or here I might want to find the normal vector between two lines. Here's one line and the other line, so that I can find the shortest distance between them. So it'd be useful to have something that would do that. Now we could find it using the scalar product, but that takes ages to do. But the vector product takes us straight there. The vector product is written as A cross B. That's why it's quite often called the cross product, and you'll hear me using that term as well in this video. We actually calculate it by calculating the determinant of a 3D matrix. And we put into this 3D matrix 3x3 matrix, three components. The first thing we put in is the I, J and K vectors. Now that might be a bit weird, but it fits in neatly and it keeps the whole thing neat and tidy. We'll show you the calculation below. Then in the second row we put in the A, X, Y and Z components, and in the third row we put in the B, X, Y and Z components. So how does that work out in practice when we do the calculation? Well, we just follow the normal way of doing a determinant. We've got the I as the component, the factor in the top left, cross out the values that are in the row and column, and that leaves us with the minor matrix there, which we're going to do the cross multiplication for. So our first component, we end up with the I vector multiplied by that determinant. Then the second component, we get the J vector multiplied by the next determinant, but of course it's negative here because remember we go positive, negative, positive, negative, yeah, AD minus BC. And then the third component will be a K vector component with the third determinant. So you'll have noticed that therefore what I've got here, the A cross B, is actually a vector, not a scalar, like the scalar product. Okay, let's work it in practice and see what happens with a particular and quite important result. Let's say that the A vector is 1, 0, 0. So that's 1 unit in the X direction, isn't it? That's actually the I vector, isn't it? And let's call the B vector 0, 1, 0. So that's 1 unit in the Y direction. So that's the J vector. If we substitute those in to the equations here, to the determinant, we get our three determinants now. So the first one, which would be this determinant, minor there, so we're going to get I multiplied by that determinant, which is 0, 0, that's 0 times 0, take away 0 times 1, so that determinant is actually 0, isn't it? And if we look at the next component here, the determinant is 1 times 0, take away 0 times 0. So again, I've got a determinant of 0 there. So if I'm looking at both of those, I've got 0 lots of I and I've got 0 lots of J. But if I look finally at the third component, well, I've got 1 times 1, take away 0 times 0. So this determinant is 1. So that's telling me I've got 1 lot of K. So A cross B here gave us K. Now that's quite an important result, because that says that if I take my I vector and I cross it with my J vector, I get my K vector. Yeah, so if I take the I vector, that's going along the X direction, and I cross it with the J vector, I actually end up with a vector that's perpendicular to both of them, the K vector. And that's the property that we're really interested in. The suggestion is that the vector product is always perpendicular to the original vectors. One other thing to know about the vector product is that it's not commutative. So let's just check that out. If I take, right, we did I cross J just now, let's do J cross I. We've changed the order of those two vectors over. These two determinants are still 0, so they're we can disregard those. But what's happened at the end here is I've now got 0 times 0 take away 1 times 1. So J cross I gives us negative K, yeah, minus 1K. So what do we find? I cross J is K, but J cross I is minus K. So this is not commutative. And if you look at it, it actually created a result in a vector in the opposite direction. Yeah, they were both in the same axis, but one went up and one went down. Now that's quite important because it opens up the whole conversation about the right hand rule and the cross product, the vector product. So we use our right hand here to visualize this, and it's just like we do in science when people start talking about the right hand rule. So if I point my first finger in the direction of my A vector, which we had before was X, wasn't it? And I point my my second finger in the direction of the B vector, which we were using just now as Y, then the resultant, the A cross B, will be in the direction of my thumb and will go up, yeah? So that's A cross B, which we know was in the Z direction, yeah? So that's the right hand rule. You've got to use the right hand, not the left hand, because it goes wrong. And it's really important in setting up your axes in 3 dimensions, because we have to do them as a right hand set. So if I pointed my first finger along the X direction, then and my second finger along the Y direction, then I should get my thumb will be in the Z direction, yeah? So this is why you often see the axes drawn in this way round, in that view, and effectively going round sort of anti-clockwise, yeah? X to Y to Z. And that's all because we have to have a right hand set. If we don't, the cross product doesn't work properly. Yeah, so if you use the left hand, it doesn't work properly. And this is an important piece of maths we're going to use all the way through. Should we prove to ourselves that the vector product is always perpendicular? Yeah, let's have a go at that. Well, if that's true to the original matrix vectors, then the A cross B dotted with the A must equal 0, and the A cross B dotted with B must equal 0, always. So let's just work that through, shall we? Let's do it with the A cross B dotted with A. So here's our cross product, and there's our A matrix. And what we're going to do, because we're multiplying them out with the dot product, we're going to take this determinant and multiply it by A. We're going to have this determinant multiplied by the Y component and this determinant multiplied by the Z component, yeah? That's what's going to happen. We just also have to bear in mind that this one's a positive, that's a negative, and that's a positive, yeah? So here we have 3 components going into our determinant, and if we multiply them out, there's our 3 brackets for our determinants. If we now expand the brackets, we've got 6 components. But what's interesting about these 6 components is that some of them are the same. So if we look at the first component, we've got AY, BZ, AX, and that's actually the same as the third component. They're just in a different order, aren't they? Where the AX, BZ, AY. So what's happened is these two have been swapped round. But this one's positive and that one's negative. So they're going to cancel out. Yeah. Similarly, the second component here, second term and the fifth term are the same, but one's positive and one's negative, so they cancel out. And finally, the fourth and the sixth are the same, but again, one's positive and one's negative, so they cancel out. So the right hand side, all of these expressions all come to 0. So that says to us that A cross B dotted with A is always 0, and you can imagine by symmetry that's also true of dotted by B is 0. So therefore the vector product being created is always perpendicular to the original vectors. So there we have it. In summary, the vector product is written as A cross B. We actually find the determinant of this 3 by 3 matrix, which expands out to that version there. The important thing is that the property is that the vector product always creates a vector perpendicular to the original vectors, and that's extremely useful for our if we're finding the normals to planes or lines. So there you have it.